Hello all. On behalf of our team, I would like to welcome you to Discover Science 2020. It's a real honor being here with you. I would like to thank everyone on the DS committee for having organized everything, making all this possible, and I really hope you enjoy this presentation. Our paper is titled Enhanced Food Safety Through Deep Learning for Food Recalls Prediction and is a joint work between University of Piraeus and Makridis. In this paper, what we want to accomplish is to reinforce the food safety procedure using deep learning techniques. In this effort of ours, we managed, besides improving accuracy in comparison with the commonly used naive seasonal models, to create a reinforcement learning framework for food recalls prediction. My name is Mavrepis, currently doing an MSc in data science and machine learning, and I work as a research assistant in University of Piraeus, but this work was led by PhD candidate Georgios Makridis under supervision of our professor Dimosthenis Kyriazis. A glance at the agenda. Firstly, we'll introduce the paper's purpose as well as the research questions surrounding it. Then, we'll do a quick literature review regarding time series forecasting, reinforcement learning, and their intersection. Afterwards, we'll briefly describe the dataset provided, all the pre-processing we did on it, and our approach to this problem. In section 4, we will present results from the experiments conducted, both in the form of graphs as well as in the form of a summary table, providing a comparison between the different deep learning techniques implemented. Finally, we will present our thoughts regarding future work while also leaving some spare time for any questions you might have. Let's get started. To understand the motivation behind this paper, we need to address the research questions and hypotheses that inspired it. First, is deep learning or reinforcement learning capable of improving the status of recalls prediction in the industry? And second, can data segregation, a technique primarily used to assert that the time series does not only have temporal linear correlations, benefit these deep learning methods if used as a data augmentation technique in cases where data collections consist of small amount of observations? What has been accomplished until today to the best of our knowledge? What presented here is an allegory. The Global Research Consortium could be a chat where everyone can share and read everyone else's ideas. In this sense, Devlin J and his colleagues used an architecture created by Google AI language team named BERT, utilizing Amazon reviews of food products to detect and predict unsafe foods with a great accuracy of 74%. An exemplary review of 117 papers in multiple industry sectors, conducted by Parmesan et al., reached to the conclusion that machine learning methods, such as artificial neural networks, support vector machines, and k-nearest neighbors, are commonly used for prediction tasks with exceptional accuracy. A truly inspiring work by Streetwieser et al. Presented the indomitable power of reinforcement learning, creating mu0, AlphaZero, AlphaGo 0, and AlphaGo, all systems capable to defeat human champions in games such as chess, Go, Shogi, and Atari classics. While games are extremely suitable for reinforcement learning agents, as most of them have many likable features such as a point system, which eliminates the need for a complex reward function, Kaloudis and his teammates incorporated reinforcement learning into the stock market by discovering a new Markov decision process, which was suitable for describing it. They managed to create an agent who made robust and profitable trading. This leads to today, here and now, where we try to define a suitable reinforcement learning agent for predicting food recalls with greater accuracy than other deep learning models. What data has been made available to us, what we did with them, and our approach to this problem. The proprietary, non-open dataset contains information regarding the daily recalls of 30 types of products from 2000 to 2019. The goal was to predict recalls in a window which was set to 4 months, as it makes sense from a business standpoint. Due to this, 2 options stand out. First, utilizing the dataset as is or resampling the data to weeks, which would not make sense, since it would still be very sparse and produce relatively large cumulative error due to multiple time steps of prediction. Second, resampling the data in months, providing stationary time series, which was tested through augmented Dickey-Fuller test, with visible patterns and a lower theoretical accumulated error of predictions, since the window has been reduced to 4 time steps. Through pertinent literature, we decided to use percentage change instead of the actual recalls number. This bridged the difference between time series, which varied significantly in multiple statistical features. Another side effect of this approach is that it also transforms non-stationary time series to stationary ones. Segregate data are time series data that reproduce various statistical properties, like the autocorrelation structure of a measured dataset. We use the produced surrogate data as a part of our original dataset, with the idea being that we could find some patterns not available in the original dataset, enriching it. This could prove very useful in datasets with small volume, velocity, and variety in multiple industry sectors. We approach this problem through different ways. Firstly, with regards to data, as a univariate problem, where only data from one time series was used to predict itself, and secondly, as a multivariate problem, utilizing all time series. In the model-wise frontier, the separation was between GlueNTS models and our reinforcement learning approach. GlueNTS is a framework that bundles components, models, and tools for time series. We used it to perform food recalls prediction and as a reference point for our reinforcement learning system. The GlueNTS models that are used are a deep autoregressive estimator, which implements an RNN-based model, a simple feed-forward network implementing a simple multi-layer perceptron, a one deep factor estimator, which uses a global RNN to learn some features across multiple time series and a local model per time series, a seasonal naive estimator, which naively predicts based on seasonality or by using the mean, and finally, a WaveNet estimator, which is a fully autoregressive and probabilistic model. After that, we created the RL components needed to solve our problem. Those elements, which will be seen in the next slide, were the environment of the agent, the reward function, the set of actions, and the agent itself. Below, the architecture of the implemented RL framework is shown. The agent, shown in the white box, acts randomly at the beginning, interacting with its environment, which is the time series itself, revealing the next actual time series value. Then the environment provides a tuple with everything necessary to the experience buffer, which acts as a mean to tackle the natural tendency of the RL agent's forgetfulness. Based on the experience and knowledge, the agent trains a deep neural network as its center of decision making, rendering the whole training process possible. A typical extension of k-fold cross-validation is the leave one out validation, which creates an even more extreme peeking into the future considering the shuffle and random split. These issues reflect a pitfall in a time series forecasting problem, as they result in a significant overlap between train and test data. Thus, the better approach is to simulate models in a walk-forward sequence, periodically retraining the model to incorporate specific chunks of data available at that point in time. This procedure is depicted in the slide. And of course, our experimentation results. In this slide, we can see multiple graphs of the various utilized models forecasting time series values for corresponding products. The blue line in each graph represents the actual time series data, while the green line is the median of prediction. Around this, we have a 50% and a 90% prediction interval shown in dark and light green correspondingly. We can see that sometimes we have impressive results, as shown in the graph number 4 at the bottom right corner. This slide conveys our experiments with numbers. Here, we compare the 4 different cases: the univariate with data segregation as an augmentation technique, the multivariate case, and the reinforcement learning approach. For each row representing a different time series, marked in green, we will find the best approach for this specific time series. For example, in row 0, multivariate DPAR achieved the best loss. Marked in blue, you will find the cases where the usage of data segregation improved the loss of the corresponding model, which happened 39 times. Finally, in yellow, we can find the cases where the RL approach achieved better results than everything else, which happened 9 out of 30 times in total. Some closing remarks. To sum up, the main contribution of this paper is twofold. Firstly, through experimentation and evaluation, we compared a variety of approaches based on deep neural networks and statistical terms, concluding to a complementary approach which consists of an RL model, providing promising results in the important and growing challenge of food safety. Secondly, we proposed and tested the utility of surrogate data as a method of dataset enrichment when data are not big, concerning the usage of ML and DL models. As far as future work is concerned, it will be focused around improving the RL time series framework, while at the same time migrating it as a service of a major food safety framework. Finally, regarding future research, it will be interesting and informative to test the statistical characteristics of its time series, in order to evaluate the difference in performance of the models and propose the corresponding adaptations and enhancements inspired by the explainable AI trend. Thank you all.